Hello everyone, and welcome to this video on how to determine the number of factors in an exploratory factor analysis in Mplus. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about structural equation modeling, factor analysis, latent class analysis, or multi-level modeling. If this is something that interests you, then please subscribe to this channel. Also, don't forget to check out the description for additional resources, including workshops that I teach for QuantFish. In this video, I want to walk you through an exploratory factor analysis in Mplus, and specifically, I want to show you how you would make a decision about how many factors to retain in an EFA in Mplus. So what criteria, what fit measures does Mplus offer that you can use to find out how many factors you should use in your exploratory factor analysis. And I'm going to do this based on a simple example. In my data file, I'm going to look at 6 different variables. 2 variables are related to a mental rotations test, so a test of spatial abilities, and the remaining 4 variables are subscales of a math test. So you can already assume, basically based on that design, that there will probably be 2 factors, one for the spatial ability measures and one for the math test measures. However, we don't know, maybe a single factor is sufficient to account for these data. And so based on this example, I want to show you how you can figure this out. So what are the things that you would look at in Mplus in order to find out, should I retain 1 factor or do I need 2 factors? So let's get started and let's take a look at that. You can see that in my analysis command, I specified type equals EFA, and then the 1 and 2 behind EFA here mean that I'm extracting both a 1-factor solution and also a 2-factor solution in Mplus that I can then compare. Next is the parallel subcommand, which allows me to run a parallel analysis. A parallel analysis serves to determine eigenvalues for sets of random variables. So random variables that have no relationship in the population, that would only correlate in sample data based on sampling error, sampling fluctuations. And so then for those random variables, we can also extract eigenvalues for the correlation matrix, and we can compare those eigenvalues for the random data to our data to see how many factors we should retain. And it's one of the nice features of Mplus that it allows you to conduct a parallel analysis for the number of factors directly here in the program. The 100 means that 100 random data sets will be simulated and the results will be averaged across those 100 data sets for the parallel analysis to give us a little bit more certainty about the results. So we want to not just do this with one set of simulated data, but we want to do this with a little bit more data so we have more solid results. And then I'm also going to request the plot option type equals plot2, which allows me to take a look at the eigenvalues for both the actual data and the parallel analysis. Next, you can see in the output that there is a warning here that says that the dataset contains cases with missing values on all variables, and these cases were not included in the analysis. So that means that there were a total number of 35 cases who did not take either the mental rotations test or the math test. They only participated in the other assessments in that study, and so that need not bother us because we still have enough data. 552 cases are still left, so that is sufficient for our analysis. When we scroll down, you can see that by default, Mplus uses a maximum likelihood factor analysis with an oblique rotation called geomin. So the factors are allowed to correlate after rotation, and that is typically what we want. So we want typically an oblique rotation, not an orthogonal rotation, because an orthogonal rotation would assume that the factors are uncorrelated, and that's typically not realistic. When we scroll down further, we can take a look at the covariance coverage, and that tells us something about missing data for those cases that did have partial data for one or more of the 6 variables. And so you can see that the minimum covariance coverage value here is 74.3% for those covariances between the mental rotations measures and the math test score. So there was about a quarter of cases who did not provide data on either MRT or math test, and so then those individuals would be lacking for computing those covariances, but we still have 74%, and so that is pretty good. And 3/4 of our sample are available for those covariances at a minimum. All the other covariance coverage values are higher, so that looks good. So we don't have a problem with too much missing data here. And then Mplus by default uses full information maximum likelihood, which is also nice, and it's an advantage over using programs such as SPSS for exploratory factor analysis, because it allows you to include more data. Whereas in SPSS, you'd have to think about how to do multiple imputation first, and then how to do your EFA with the imputed data sets. And so here it's more straightforward because Mplus uses full information maximum likelihood for addressing missing data, and then there's nothing else that you have to do in the analysis. Next, we have some descriptive statistics here, and then below that is where the model fit information begins. So now we find information on how many factors we should retain. And you can see that the 1-factor model has a very high chi-square value for the maximum likelihood factor analysis. 287.723 is the chi-square value with 9 degrees of freedom, and that's highly statistically significant, indicating that the 1-factor model is rejected clearly. So a significant chi-square value means that the model does not fit. There's a significant discrepancy between the observed correlation structure and the correlation structure that we would expect under a 1-factor model. So 1 factor is not enough to account for the correlations between those 6 variables. A 2-factor model has a much lower chi-square. You can see then the chi-square for a 2-factor model is only 9.46 with 4 degrees of freedom, and the p-value is 0.05. So that's right at the border of significance. So strictly speaking, we would still have to reject that model, because 0.05 is typically where we still reject an alpha level of 0.05, and p is 0.05 or smaller. We reject the null hypothesis of an exact model fit. However, you can see that the 2-factor model is a lot better. And also with only 6 variables, there's really not much more that we can extract, at least not in an EFA. And so we would have to go here with the 2-factor model. And as we will see, according to other criteria, it actually fits pretty reasonably well. Mplus also provides a chi-square difference test for comparing the different factor models. So here 1-factor against 2-factor models, and you can see that the chi-square difference value is 278 with 5 degrees of freedom. So that's the difference here between those chi-square values, and then the difference in the degrees of freedom is 5. You can see that difference chi-square value is also statistically significant, indicating that a 2-factor model fits significantly better than a 1-factor model. So it's far better. This is a huge chi-square difference for 2 factors versus 1 factor. So it's a huge improvement when we add a second factor. Next, we can look at more traditional criteria for EFA model fit or model comparisons, and that's related to the eigenvalues. Remember that there is a criterion for factor selection with eigenvalues that says we select all factors that have an eigenvalue greater than 1. That's also called the Geiser criterion. And so in this case, then we would select 2 factors because there are 2 eigenvalues in our list that are greater than 1. The third eigenvalue is clearly below 1. So the eigenvalue greater than 1 criterion here would tell us to retain 2 factors rather than just 1 factor. Also, you get the eigenvalues from the parallel analysis averaged across those 100 replications, those 100 simulations that were conducted for the parallel analysis. And you can see that even for random data, we have eigenvalues that are greater than 1. Here specifically, there would be 3 eigenvalues that would be greater than 1. So in other words, the eigenvalue greater than 1 criterion may not be the best because even random data will produce eigenvalues that are greater than 1. However, what is more solid in terms of the eigenvalue comparison is comparing the eigenvalues from the actual data here above to the eigenvalues from the parallel analysis and then looking at where those eigenvalue scree plots intersect. And so the best method to do that is graphically with a scree plot, and we do get the scree plot in Mplus when we click on plot, view plots, and then eigenvalues for exploratory factor analysis is the only option here. We click on view, and then you can see we get this nice plot with the sample eigenvalues in red for our actual data. So that's the eigenvalue distribution for our mental rotations and math test scores. And here you can see that there's an intersection with the eigenvalues from the parallel analysis, which are shown here in black. And so you can see that they intersect between 2 and 3 factors, which means we're going to use 2 factors. According to this criterion, we would choose as many factors as there are eigenvalues above the curve for the parallel analysis. So above that black curve here, we have 2 eigenvalues for the real data, and so that would then indicate that we should retain 2 factors. Okay, so that's also a good criterion to look at in addition to the chi-square value. Let's go back to our output file. And so now we can scroll down further and we can see here that we also get more detailed fit statistics for each solution. So the first solution that is shown by Mplus is the 1-factor solution. And here we find the log likelihood values. We also find information criteria that we could also use to compare different factor solutions. So for example, we could look at the AIC or BIC values for different numbers of factors, and then we would select based on that criterion the factor solution that has the lowest value of either AIC if we're using that or BIC if we're using that as our criterion. And you could do the same thing as with a scree plot. You could plot the AIC values for different numbers of factors. You could plot the BIC values for different numbers of factors and then look at where you find a minimum. You get the chi-square test of model fit again. This is the one that we've already seen, which led us to the conclusion that the 1-factor model here is clearly rejected. You can see also the RMSEA fit index, which is a classical fit index for structural equation modeling and confirmatory factor analysis. This that can also be looked at for EFA also indicates a poor fitting model. This is a very terrible looking RMSEA. The estimate should be 0.05 or smaller for a good model, and then the 90% confidence interval also should be much lower than what it is here. So that looks terrible. Also CFI and TLI values that are also commonly used in SEM and CFA also look terrible. They should be above 0.95 for a good model, and they are way lower than that here. The chi-square test for the baseline model is a model that's very basic, that assumes that there are no covariances between the variables, and that of course is an even more terrible fit than our target model. You can see that target model has already a terrible chi-square of 287. The baseline model is even worse because it assumes that the variables are uncorrelated, which is totally not the case in our example. And then finally, the SRMR value is given here. This is a fit index that summarizes the residuals, meaning the discrepancies between the observed correlation structure and the model implied correlation structure in a single standardized measure. And a common rule of thumb for that is that it should be smaller than 0.05, which here it is clearly larger. So all these indices clearly indicate that a one-factor model here is not a good model, that you shouldn't use that model. So let's take a look at the two-factor solution. Here you can see the factor loadings for the one-factor model. And here you can also see that this isn't a good model because you can see the MRT variables, they have pretty modest loadings on that single factor. The math variables load pretty strongly. So you could say, okay, there's clearly a difference between the math variables and the MRT variables because they don't load really well here. So we need a separate factor for those variables. Scrolling further down, we get to the two-factor solution. And again, you get the same set of fit indices for the two-factor solution here, the information criteria, and then the chi-square that we've already seen, which was borderline significant, a lot better than the chi-square for the single-factor model. You can see the RMSEA now looks good. 0.05 is not a bad value for an RMSEA. CFI and TLI look good. They're both greater than 0.95. And the SRMR looks very good here as well, with an average standardized residual of 0.01, which is pretty minimal. Looking at the rotated factor loadings with oblique rotation, you can see that there is another indicator here that the two-factor model really is the way to go, because you can see that we get a very clean, very nice, simple structure. Here you can see that the first factor now is a factor that loads the MRT1 and MRT2 spatial ability test score variables with strong loadings. Both these loadings are above 0.8. And you can see that the loadings on the second factor for these MRT variables are essentially or exactly zero. And that's perfect. That's exactly what we want. That's like a simple structure where really this factor clearly is an MRT factor and those variables have nothing to do with the second factor. Okay. And then likewise, for the second factor, we find very clear loadings of the math factors that are between 0.7 and 0.82, or actually there's one that's lower for the last subscale, which is only 0.64, which is not so great, but it's still a pretty substantial loading. So clearly those four math variables, they have the stronger loadings on the second factor. They have loadings that are very close to zero on the first factor. So again, this confirms a simple structure for the two-factor solution that is clearly interpretable, that leads to clearly interpretable factors, where we would interpret the first factor as a mental rotations factor and the second factor as a math factor. None of the cross loadings are significant. You can see there are little stars here. These indicate statistical significance at the 5% alpha level, and all of the intended loadings are significant. You can see that's the case for MRT and then also for the math variables. All these have a star, and none of the cross loadings here have a star, meaning they're all non-significant. They are not significantly different from zero, which is what we want. Also, the factor correlation is reasonable. You can see that it's 0.333, so it's not too high. There is clear discriminant validity between the two factors. The mental rotations factor 1 and the math factor 2 are related, as we would expect. However, this is a modest correlation, a moderate effect size in terms of Cohen's guidelines for correlations as effect sizes. And so here we find that there's clear discriminant validity between those two factors. So overall, this is how you would do model fit assessment in EFA, in Mplus. Those are the criteria that you can use, and typically that is very helpful because you have a whole bunch of criteria that you can look at. Classical EFA fit measures such as eigenvalues and parallel analysis, as well as more modern, so to say, fit statistics such as a chi-square, and then other fit statistics that we commonly use in structural equation modeling. I hope you found this tutorial useful to learn more about how to select the number of factors in an EFA in Mplus. If you did, then please subscribe to this channel and don't forget to check out the description for additional resources, and I'll see you next time.